Now, look, last class, what we were going on with was this part where we were discussing the ideal gas equation, right? And over here, what we mainly did was we found out a bunch of proportionalities, right? We looked at the Boyle's law, we looked at the Charles law, we looked at the pressure law. And all of these three laws we combined together and we formed the ideal gas law, which states PV, product of pressure and volume, is proportional to the constant nRT. Okay, so this equation is what we ultimately found out by joining the relationship between PV and T. We removed the proportionality and we ended up finding the constants to be moles, time, reaction gas constant. This reaction gas constant again was experimentally found out R, and there is no specific mathematical derivation for this, right? You can experimentally put in a bunch of values. You can plot PV against temperature on a graph. Whatever gradient you get is simply N times R. And if N is known to you, that is the number of mole that you're working with, you can equate NR to the gradient that you find out, and simply you make R the subject and you get the reaction gas constant. This is how the numbers come out to be.
Yeah.
Great. So now what we will do is look at moles and Avogadro's constant. Okay. So now what happens with moles is we start off with the definition of it. Now you have studied this in chemistry, you have studied this in IGCSE chemistry as well, and very little in physics. So if I had to define this to you, uh, a basic crude definition would simply be what is the amount of any substance that we define as mole. Okay, so whenever you're working with any amount of substance, we start defining it as moles. Okay, the more amount I have, the more moles I have, right? So now how do you technically define that? What is the technical definition of it? The technical definition of it is it is the amount containing as many atoms as there are for a 12 gram of carbon molecule. What does that mean? It seems very confusing. It seems
Sir,
like a
do
very
we need to
lengthy.
like
Yeah.
memorize this definition?
Sorry.
Do we need to memorize this definition
Yes.
or?
Mole you need to. Yes. Mole you need to memorize and understand. Now, this is telling you, if I just qualitatively describe what mole is over here, according to this definition, it is telling you if I have, let's say, a bunch of carbon over here, and I take a part of it, which is 12 gram. So I scoop out 12 gram of carbon. Okay, I take 12 gram of carbon, and however many atoms there are in this 12 gram of carbon, those number of atoms define 1 mole. So when I scoop out 12 gram of carbon, however many atoms there are in a 12 gram of carbon sample, that is the definition of 1 mole. And do you know the number of particles for 1 mole? It is simply 6.02 into 10 to the power of 23 atoms. Okay. Now you will probably ask me, why are we talking with respect to carbon? Is it necessary to talk with respect to carbon? Well, this is the standard that the scientists figured. This is the standard that the scientists figured to consider as the standard definition. So they took carbon as it's the most pure, abundant element that we have all around us. So they thought, why not define mole with respect to carbon? But my question to you guys, or your question to me is, can I define the same thing that is mole in terms of any other element? Yes, we can. How? Take any element. Anything. Okay, 1479. What are these, by the way? The mass number. Okay, the mass number, atomic mass unit. You've heard or learned about this previously in chemistry. So this is the mass number. What does this mean? However many number of protons and neutrons they have. So this is the mass number. And this also tells you 1 mole of hydrogen, the weight of 1 mole of hydrogen is 1 gram. The weight of 1 mole of helium is 4 gram. The weight of 1 mole of lithium is 7 gram. So while this mass number tells you how many proton and neutron the element has, that is the atomic mass unit, it also tells you, it also tells you how many grams 1 mole of each substance have. Okay? So now the conversation is, if I say 1 mole is the number of particle in 4 gram of helium, is it an accurate description of 1 mole? Is this also a definition of 1 mole? Yes, it is. So while you can say this with respect to carbon, I can also say this. I can also say that however many atoms there are in 4 grams of helium, that defines 1 mole. And we'll look into the maths of it to prove it to all of us. Okay? So do we understand what 1 mole is? It is simply the number of atoms that there are in either 1 gram of hydrogen or 4 gram of helium or 7 gram of lithium or 9 gram of beryllium or 12 gram of carbon. Now this is the standard definition. So we write this. Is this part clear? Yeah.
Yes.
Okay. So now in the orange over here that I've written, this is simply to help you guys understand what 1 mole is. A bit of an added description because when I bring into the conversation that it's related to carbon, people start asking me, why is it related to carbon? What is the relevance of carbon? And my answer is, it is not just carbon, it can be any element. It doesn't matter. It's just that if it's 12 gram for carbon, it is a different amount of grams for different element. It's just that. Now, you have learned about this conversion in chemistry. If you have not, I will repeat this. Now, number of moles of any gas in any given volume is the same as 1 mole equals to 24 dm cube. Doesn't matter what gas you take, does not matter what gas you're working with, what substance it is, what element it is, does not matter at all. If I have 1 mole of any gas, it will occupy what volume? Any gas. It will always occupy 24 dm cube or 24,000 cm cube. Okay. So this is the conversion between dm cube and cm cube multiplied by 1,000. So this is the volume that any given gas worth 1 mole of atoms will occupy. That is 6.02 into 10 to the power 23 atoms. Okay. So those atoms for any gas will always occupy 24 dm cube. If that's clear, if I give you an example, find the moles of 50 cm cube of chlorine gas. How will you find it out? You simply say that the 50 cm cube I converted directly. I can work with cm cube as well, doesn't matter. If I'm working with cm cube, I will say 50 divided by 24,000. And I get the answer over here. Okay, so it's okay to work with cm cube. It's also okay to work with dm cube. Does not matter. It does not matter what unit you're working with because the units get cancelled off. So now I can convert cm cube to dm cube and say, okay, I'm
So, sir, do we
dividing.
just
Yeah.
like use the formulas we learned in chemistry?
Yes. So this conversion that you're seeing, it is the same formula as you have in chemistry. Yes. So you can use that. So now, when you're working with 50 cm cube, you can convert to dm cube by dividing by 1000, and you divide that volume by 24, and you get the number of moles. Okay? Because 24 dm cube describes 1 mole, right? So if you have more than 24 dm cube over here, that means more than 1 mole of gas. If it's less than 1 mole of gas, that is less than 24 dm cube, your answer is less than 1 mole. Very simple calculation over here. Very simple calculation. So now, if that is the conversation ultimately, we can move on with finding the number of moles in a different way. We found out the number of moles by dividing the volume of gas. That's one way to work with it, right? And the other way to work with it is by considering the number of atoms itself. Do you guys know from chemistry? Again, I repeat this, 1 mole of any substance will have 6.02 into 10 to the power of 23 atoms or particles. Clear? Now, if I tell you that I have, let's say, not 6.02 to 10 to the power 23, but well, I multiply with 2 and I say 12.04 into 10 to the power 23 atoms. How many moles do I have over here? How many moles of any substance do I have over here? These are the number of particles I have. Your simple answer is I'll divide this 12.04 into 10 to the power 23 divided by 6.02 into 10 to the power 23. My answer comes out to be 2. Since 1 mole has these many particles, I divide whatever amount of particle I have by this. What do I ultimately get? The number of moles. Okay? The number of moles. This is what I ultimately get. So 2 moles. If I have 12.04 into 10 to the power 23 atoms, I have 2 moles. So this is a simple way to find the moles as well. Number of particles that you have at hand or measuring divided by the Avogadro's constant. That's 6.02 into 10 to the power 23. And you get what? The number of moles. Moles. Okay? Next. Now, this is where it's interesting. This is where the math is involved. This is where I get to prove certain things to you. How to find out the Avogadro's constant. Let's find it out. Now, when you work with chemistry in the elements, again, I write this helium, B, C, and O, right? So you have the mass number, and you also have the atomic number, the number of electrons, protons that it has. So now, in case of hydrogen, it is 1, 4, 7, 9, 11, so on and so forth, 12, 14, 16, so on and so forth, right? Now, if this is the case, if this is the case with the mass number, what does the mass number tell me? That 1 mole of hydrogen, the one thing that it tells me, 1 mole, I'm just working with, let's say, let's work with helium, okay? Let's work with helium. If I work with helium, what does mass number tell me? 1 mole of helium is worth 4 grams. The other thing it tells me is 1 atom of helium, right? 1 atom of helium has A, 2 electrons, B, it has in the nucleus 2 protons and 2 neutrons, or to be more simple, the nucleon number is 4. That is, the mass number is 4. Okay? So over here, I have 4 subatomic particles in the nucleus. So 4U is the mass of the atom. The electrons, has negligible mass in comparison.
Yeah.
So the mass really comes from the nucleons, right? So, sorry,
It's not this over.
I can't really hear you.
Make a straight line with both hands.
All right. So look, over here, when you're working with the nucleus, how many subatomic particles do you have inside? Four. So what is the entire mass of the atom? Four times the mass of each of the subatomic particle, which is denoted as U. All right. So the mass of a neutron is U. The mass of a proton is also U. This is something that we just know of. Okay. This is something that we know of. Okay. And I'll work with this idea over here on the side, on the right hand side. But first, I'm just establishing that the mass of the atom comes from the nucleon and depends on how many subatomic particles I have in the nucleon. That is the proton and the neutron. If I'm talking with respect to helium, it is four. So two things I get to know from this list. One, 1 mole has 4 grams of helium, and one atom of helium has a mass worth 4 times U. U is the mass of a proton or a neutron. If this is clear, I can move on. Now look, on the right hand side. We express the mass of any atom with respect to U. Okay? So basically over here, it's 1U, 4U, 7U, 9U, 11U, 12U, so on and so forth. So one atom of helium has a mass worth 4 times U. One atom of lithium has a mass worth 7 times U. Now, this U is the mass of a proton or a neutron. Understand that. Okay? And it's well established. Okay? Now look. So now, what is the value of this U? This is given to us. This is what scientists have figured out at some
So,
point in their
so
life.
this is like similar to what we did in nuclear physics in AS thing.
Yes. I mean, over there, you worked with binding energy, you worked with conversion of. Did you guys have what was it called? What was the topic called?
Nuclear physics.
Particle physics.
What was the other one you said right now?
Particle physics.
Yes, particle physics. Right. So yeah, you do come across this over there as well. So over here right now in A2, you do have nuclear physics. And there you work with binding energy, a few other things. And when you worked with AS, you worked with subatomic particles, quarks, and a lot of other ideas. Yes. So, but I don't think, was this covered, the proof of Avogadro's constant in your AS? No, right? Was it? I'm not sure.
No, it wasn't.
No. Okay. I mean, I don't know with other syllabuses, but as far as I remember, with we're going to start teaching AS as well, but we haven't come across this in AS as well. So now the conversation is, if I have established this, that is atomic mass unit, one atomic mass unit has a mass of 1.66 into 10 to the power minus 27 kg. That is the mass of one proton or one neutron. Granted, you know this, understand this, believe this. We move on to the next thing. By the way, mass of electron is negligible, so we don't consider this towards the mass of an atom. You know this? Fair enough. Now, whenever we have any atom and we say its mass is 1U, 4U, 7U, it's basically saying number of proton plus neutron, that is, let's say helium is 4 times its atomic mass unit, U. Okay, this is the total mass of one atom. One atom. Moving on, we know a mole is simply the number of atoms in exactly 12 grams of carbon. Can this be said with respect to helium, nitrogen, oxygen? Yes. But we are just taking carbon as the standard and working with that idea. Now look, if I work with carbon over here, atomic mass of carbon is what? 12U. Agreed? Now, 1 mole can be defined as 1 mole can be defined as the number of particles in 12 grams of carbon, right? How do we find that number of particles? We take the total mass of 1 mole of carbon, which is what? 12 grams. We establish that when defining 1 mole. 1 mole is equals to the number of particles in 12 gram of a carbon sample. So we take this 12 gram over here, since 12 gram is simply 1 mole of carbon. And I converted this into kg, that's why it's 0.12, 0.012, sorry. Fair enough. What do we divide this by? We divide this by the mass of one carbon atom. And one carbon atom has a mass of 12 times 1.66 into 10 to the power of minus 27. That is 12 times U. 12 is the number of subatomic particles in the nucleus times U. So this is where the mass is of one atom. So this is mass of 1 mole of carbon, and this is mass of one atom of carbon. Okay? So what do we ultimately get? The number of particles in 1 mole. When I have 12 grams of carbon and divide by the mass of one atom of carbon, I ultimately get how many atoms there are in 12 grams of carbon. This is 6.02 into 10 to the power 23. Okay? This is how we get the Avogadro's constant. Can you do the same thing with helium, nitrogen, oxygen, all other elements? Yes, you can. You just change the 12U to, let's say, 14U, 16U, whatever element you're working with, you take their mass number and work with that. So that's the proof of Avogadro's constant. Hopefully, we understand the calculation. Now, I can also do the opposite thing. I can also do the opposite thing and say, I know the mass of, the mass number of carbon is what? 12U. Okay? And I know 1 mole of carbon has how many particles? 6.02 into 10 to the power of 23. So, how much of a mass will 1 mole of a carbon have? Very simple. 12 times 1.66 10 to the power minus 27 mass of one carbon atom times however many particles there should be in 1 mole of any substance, which is 6.02 into 10 to the power 23. If you do this calculation, do you know what you will find? Your answer will be 12 grams. Your answer will be 12 grams or 0.01199 kg or approximately 0.012 kg. So it works either way around. It's maths. It works either way around. It doesn't matter what you start off with. You want to find how many particles there are? Well, you do this. You want to find how much of a mass 1 mole of carbon would have? This is the calculation you have. So this is how this makes sense. That this mass number tells both what is the atomic mass number of all of these elements, also what is the mass in grams of each of these elements for 1 mole of all the substance. So this is the great thing about moles. And this is how the amount moles or quantity moles came out to be. This is the calculation behind it. Okay? And this is a very neat calculation because it works both way around. Okay, and for all elements, not just carbon. I showed with respect to carbon, but you can do the same thing with everything, every other element. Granted that is clear, hopefully no question over there. I'll move on to the kinetic theory of gas. This is the main part. This is where the broad derivation is. So the first thing with kinetic theory of gas, I mean, this is the theory part when we do the derivation with yeah, kinetic gas theory derivation. This is where most of the maths is. Yeah, that's going to be a bit complicated. So ask me if you get confused anywhere. Now look, the kinetic gas theory is basically a theory which describes the motion of gases, how gases behave, and when we work with ideal gases, what are the assumptions we consider, right? Those are the things we are going to discuss just in theory. So according to Brownian motion, it says particles are in constant random motion, okay? Constant random motion in a fluid, and fluids describe both liquid and a gas. Now, due to the movement of the fluid molecules, that is, the molecules inside, the atoms inside, they keep colliding and changing their own trajectory. This can be observed under a microscope. So when you have, let's say, a still bucket of water and you put very small, very light identifiable particles, let's say, well, leaves, let's say, but really light leaves, you will see even if there is no wind, the leaf will move around on the surface of the water. Why? Because of Brownian motion. Because the particles are always in constant random motion in any fluid, in gases, in liquids as well. Okay, so this is something we observe under the microscope. There's random motion, even without any external factor. Now, molecules in a fluid are always in constant random motion. Fair enough, this we discussed. Now, there are two ways to look about the kinetic gas theory. One is the microscopic lens, and with respect to the microscopic properties, we see that, well, we observe the mass of the particles and we observe the speed of the particles. When we're observing the atoms itself, we observe the mass of the particles, the speed of the particles, and those two are very important variables that we'll be working with when deriving everything. And when we look at the macroscopic lens, that means what is the effect of the mass of the atoms, the speed of the atoms, and their movement? What is the effect of that? We see the effect as pressure and volume. So you have a box, a bunch of, not a bunch, but I mean, there's a gas inside. Now, all of the particles have a mass and a speed. And what is the end result of that? The end result is it exerts a pressure and occupies a volume. That is what I mean microscopic and macroscopic properties that we look into. Now, for the kinetic gas theory or ideal gases, what are the assumptions we make? There are a few assumptions that we make, okay? And you're going to look into this. Why? Because none of the formulas, PV is equals to nRT, or those relationships, individual relationship between pressure, volume, pressure, temperature, temperature, volume, none of these would work if these assumptions are not true, are not considered. Okay, what are the assumptions? Now, the first assumption is molecules of gases act like perfect spheres, causing a completely elastic collision. Why is this necessary? Because we consider the momentum to be conserved inside, we consider the energy to be conserved inside. Let's say I take a box, and you will observe this when we derive uh, the pressure formula. When we derive the pressure formula, you'll observe this, and also the kinetic energy formula. During those derivation, we make this assumption because we consider there to be particles inside, and we consider these particles to collide with the walls of the container. And if that happens, now we have to consider momentum to be conserved so that we can consider this equation mv minus mu divided by time is the force exerted. Now we can't work with these ideas if energy is being lost in the process of collision. Momentum needs to be conserved. Energy needs to be conserved in the process. Because if energy is being lost to the surrounding, then it doesn't make sense to use this equation because it's not going to give you the accurate answer. So you will see this later on, how we use momentum, how we use other formulas to come to the ultimate formula of kinetic energy and of pressure. So it's very important to consider that momentum is conserved. And for that, it should be completely elastic collision. What are elastic collisions? Energy is not lost, momentum is conserved. Momentum is in general always conserved, but yeah, energy is also conserved. Okay, so that's very important for our kinetic gas theory. Okay, there are also perfect spheres that results in the elastic collision. Now, volume of molecules are negligible compared to the container volume. Why is that necessary? You have a box and you have particles inside. Now, when we do the calculation, you will see, if I just give you a glimpse, the ultimate formula, very long. Look at this over here. So we do consider over here the volume, okay, the volume of the box, right? We consider the volume of the box. L cube is the volume of the box. Now, if the particles are really big, what happens? The amount of space it can travel decreases. If all of these particles are really large, what happens? If this is length, 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 and the volume is L cube, and the particles that I have over here is really large, the problem is the volume available to this particle is not L cube. The volume available to them is L cube minus the volume of sphere or volume of particles. This is a question that can come your way as well, where you have to find the volume available to the particles by minusing or subtracting the volume of particles. But anyways, in general, we consider the volume available to the particles as L cube. But is it truly the volume available to the particles? No. Particles itself occupy some space. How much space? 4 by 3 by r cube, right? Times the number of particles, however many particles you have. So ultimately, the space available to them is L cube minus volume. But for the kinetic gas theory, what do we consider? We consider the particles to have negligible volume. Why is that necessary? Because of the ultimate formula that we derive. There we consider the volume to be L cube. And if that's not possible, if the volume of the particles are really large, because we have to subtract the volume of the particles from L cube. Do we get that idea? So it's very important to make this assumption that we have a really large volume available to us and the atoms itself are very, 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 very small, negligible. Such that if I just bring it to perspective, if I just put all the atoms together, it will simply occupy a small corner of the box. This is how small the atom should be. It will only occupy a small corner of the box if everything is smooshed together into a small space. So that so my assumption over here is very important. Next assumption, what do we have? The time of contact while collision is negligible compared to the time in between. Okay. So over here, when I have atoms going back and forth, colliding with all of the walls, what we have is, in reality, even the time of collision between the wall and the spherical particle that we have, the atoms, the time of collision is actually, in reality, it's not just an assumption. In reality, it is very small. It is very small. It collides with the wall for a very, very small amount of time. And we make this assumption into being negligible, meaning pretty much zero. Why do we do that? Because when we find the change in momentum in calculation, all of these assumptions will actually make more sense to you when we do the derivation, because you will see each of these assumptions coming into play. So when we do this derivation, what we consider for the time taken for the collision between the particle and the wall, we take that time taken to be the entire journey of the particle, not the time of collision. Why? Because we consider the time of collision to be pretty much negligible, zero. So we take the time it takes for a particle to go from one end of the box to another end of the box and coming back. This is the time we take for the change in momentum that takes place at the wall. So mv minus mu by t, you know what this time is? This time is the time taken for the particle for the entire journey, not the collision. And it is very confusing. If you're confused about this, rightfully so. And I'll explain again later on when doing the derivation why we do this. This is the long as derivation, explanation that I have. And I will explain all of this. But point is, I consider the kinetic theory of gases assume that the collision at the wall is negligible. So we don't consider it into the calculation. We don't consider in the calculation. That is why this assumption is made. Okay? That the collision between particle and wall is negligible. It just makes our calculation easier. Fourth thing, there are no intermolecular forces. In ideal gases, we also assume that the gases have zero energy, potential energy between themselves. Why do we consider this? The reason we basically consider this is you will later on see in the thermodynamics chapter that we define internal energy of any substance, any gas, with respect to how much heat is provided to it and how much work is done on it. These two things. Okay. So we ultimately only consider the internal energy of gases with respect to the temperature it has. You and I will show this to you later on as well. The internal energy of any substance is simply related to its temperature because temperature is now related to kinetic energy. We don't consider potential energy when talking about internal energy of any substance. And that is why this assumption of them having zero intermolecular force is important. Why? Because we assume the potential energy between every one of the particles to be zero. That is why this assumption is important that there is no intermolecular forces. Yes. Okay. So when you have zero intermolecular forces, your potential energy is zero. That is why this assumption is important. Last, last we have molecules are in constant random motion. This is simply the basic definition of Brownian motion. So this is a true assumption that particles are always in constant random motion, and this is true. Okay, all of these assumptions I have tried my best to explain to you with physics intuition right now, even though you have not seen these assumptions play out in the derivation. So if you're still confused about any of these points, when you see the derivation, hopefully it will make more sense. So wait, I'll delete this and we'll get to the important part. First thing we want to define is Boltzmann constant. What is, does this have any physical, uh, what do you call it? Physical essence to it? No, it's simply for the convenience of it. We have described a constant. How? Look at this. A Boltzmann constant is simply R divided by number of atoms in 1 mole, that is Avogadro's constant. So R, if I give you the value, is reaction gas constant. It's a constant that was experimentally found out. I showed you guys above how. And Na is the Avogadro's constant, number of atoms in 1 mole. So we define Boltzmann constant as R divided by NA. Okay, so the reason we do this is because you'll see over here to get another formula, just to make our lives a bit easier with the calculation. So we calculate if we only know n, number of particles, and k, that is Boltzmann constant, which we have described as R by Na, and we know the thermodynamic temperature, and let's say I know the volume, it's easy for me to find the pressure. Right, so calculation becomes easier. That's why we have defined a different constant by dividing R by Na. Nothing else. There's no physical essence to it, really. Okay, so basically the Boltzmann constant, if I find out, and you will see when doing the calculation, K really does help you. The Boltzmann constant really does help you because you just need to type in very few numbers now. You just need to consider the N, the K, the T, and you get the answer. Okay, so anyways, the value of K can be found out by dividing reaction gas constant, which is 8.31, divided by Avogadro's constant, and this is the answer. This is your Boltzmann constant. This is given in your formula sheet, uh, constant sheet. I mean, it's the same paper. So before you do start your paper, you will see a sheet. Everything's there. You've done AS, so you know by now. Now, what do you guys need to understand in terms of the derivation right now? Do you guys know this formula, ideal gas formula? Yes? Then great. If I just break this down, above, when explaining moles, did I show you guys that mole is equal to number of particle available to be divided by Avogadro's constant? So if I have 12.04 into 10 to the power 23 atoms available to me, how many moles are in here? I divided by the number of atoms in 1 mole, which is 6.02 into 10 to the power 23, and I get 2 moles. So is this a valid equation for finding moles? Yes, it is. Can I replace this over here instead of mole? Yes, I can. It's a valid substitution, my friend. So now when I do that, what do I have? PV is equals to number of atoms available to me, let's say in a container, divided by Avogadro's constant times R times T. Can I change this into K? Yes, I can. I have explained what K is. Boltzmann constant is explained as reaction gas constant divided by Avogadro's constant. Hence, I can simply write the formula as PV is equals to number of atoms available to me times K times thermodynamic temperature T. Is that clear? So this is a new formula that you guys have. Do you guys need to memorize this? Well, you will automatically memorize this without even trying. Trust me. When you work with the formula, you automatically memorize it. And you don't even need to memorize. Understand how it's derived. I simply broke the moles down into N by Na, and I replaced R by Avogadro's constant with K. That's how I found out. Simple. PV is equals to NKT. Remember, important. You'll often need this to do the maths. Now comes the real part. This is the real deal, and this is one of the most important part of ideal gas. One is this, the other is I explained to you guys how the last class yesterday. I showed you guys the graphs. You know, the relation between pressure, volume, temperature, all of those graphs. That's very important. This is very important. Deriving kinetic gas theory. Pay attention to this. Even later on, focus on this to understand how the derivations are done. They will often ask you to derivation. Okay. So, if I just show you guys what ultimately we're deriving, this and this, you could say. Okay, these are the two formulas I'm deriving. This is for the derivation of this. But ultimately, this is what I'm getting at. How to describe pressure with respect to these variables. Speed of the particle, number of atoms I have, or number of particles I have, mass of the particle, and the volume I have. Remember, I told you guys the microscopic properties and macroscopic properties. Why did I do that? There's a reason. There's a reason. The microscopic properties available to you is mass of the particle and the velocity of the particle. And what does that result in? The macroscopic properties. The pressure as a result, and the volume occupied as a result. Is that clear? So this is why, right before starting today's class, I explained that or showed you guys that. Okay. So this is ultimately what I want to get to. And since you have a destination in mind, hopefully the derivation will make a bit more sense, which is pretty long. Look, Emma, half of it is long because I've just written extra stuffs. So look, as gas molecules are moving in constant random motion, they will hit the walls of the container and go through a change of momentum in each of those collisions. Now, this exerts a force on the wall, and the force causes the pressure. We discussed this last class as well when we discussed the graphs. Now, in this derivation, we will pretty much just find out the equation to get a pressure. But in doing so, we will find out 3, 4 other smaller equation which will also be helpful to us. Ultimately, what are we getting? A pressure formula with respect to mass, speed of particles. Okay, I showed you guys the formula, and that is what we're getting at. How do we get to that pressure formula? Goal, okay, goal pressure formula with respect to WRT, you will often see in some places, not always. And WRT basically means with respect to. Okay, I'm just telling you guys so that when you read documents, it's easier for you to understand. So, with respect to what? I want a pressure formula with respect to speed of the particles, mass of the particles, number of particles, and the volume occupied. This is what I want to get to. Let's start. Step one. My step one is I want to take a box of which I want to find the pressure exerted from the inside. Okay. From the inside, due to the particles, what is the pressure exerted on the box? So due to this particle, what is the pressure exerted on the box? And I have a bunch of particles inside. I have what? A bunch of particles inside. Let's say one bowl of gas. 6.02 to 10 to the power 23 particles inside. But before I work with so many particles, step one, consider one particle. And we will eventually find out what pressure is being applied due to one particle and then multiply with the rest of the particles. Do we get the trail of thoughts? Do we get the trail of thought? Fair enough. Start. Step one, consider a cube of length L on each side. That's the first thing we do. So I have taken a box on which we measure the pressure, and all of the sides are of length L. Clear? Great. Now, molecules in reality take a random route on, inside the box. You see this random motion of the particle? This is what happens in reality. It can go here, 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 here. It can go anywhere. Doesn't matter. This is what happens in reality. But when I'm deriving the formula and we are considering one particle, right? I'm considering what particle? One particle. I will simply assume the motion of the particle to be a straight motion. It goes from, let's say, point A to point B and back to point A. This is the simplified motion of one particle. If I just have one particle inside and it's not colliding with multiple other particles, I can simply model the entire motion as a straight line, as a 2D line. This is what 2D. This goes here straight up and comes back. Okay, are we agreeing with this assumption? We have one particle, it takes a straight path, hits the wall, comes back. This is the path we have defined. Great. What is step two? So this is part of step one. Step two, what do? We want to find the change in momentum. We want to find the change in momentum. Okay. So let's define rightwards as positive, leftwards as negative. Okay. Now look, as the particle with mass m and a velocity c travels in the rightward direction, it will hit the wall and go through a change in momentum. Is that something we can agree on? Hopefully so. Hopefully so. So if there's a wall over here, that is, I'll shape the wall. I'm talking about this one. Okay? Hopefully you understand that. Particle goes, hits with momentum mv positive, comes back with momentum minus mv. Are we clear on this? Can we agree on this? Okay, fair enough. So a particle comes in with positive mv momentum and gets back with negative mv momentum. What is a change in momentum, my friend? Final minus initial. Okay, final is minus mc. I mean, this should be c. I'm describing the velocity as c. Minus mc, minus mc. What is the change in momentum of the particle? Negative to mc. Clear? This is the change in momentum of what? Particle. But. I want to know the force exerted on the wall. I don't care what change in momentum the particle went through. I want to know what the change in momentum for the wall is. The change in momentum of the wall is simply positive 2mc. If the particle over here exerts a force on the wall on the rightwards direction, the wall exerts a force on the ball in the leftward direction. So if the change of momentum of the particle is negative 2mc, the opposite is the change of momentum of the wall, which is positive 2mc. Okay? Is there any confusion about this simple step? That the change in momentum of the wall is positive 2mc. Clear on that? And this is what we are going to, yeah.
Yes, clear.
Okay. So now moving on with that idea, I know the change in momentum of the wall. Let's now find the force on the wall. Okay. How do we find the force on the wall? Force on the wall is explained as impulse by time, or you can say change in momentum by time. Okay. And this change in momentum we found out to be 2mc. And what is the time? Time of collision, right? That is usually what we take as the time. Time of collision. Right? So we know the change in momentum, but I don't know the time of collision or how long it takes for the particle to be in contact with the wall. So step 3, find the time of collision. But how on earth do I find that? I have a wall, I have the particle. There is literally no way to find the time of collision. That's the problem over here. There is literally no way to find out the time of collision over here, mathematically speaking, or even by observation. As I told you guys towards the beginning, time of collision is considered to be negligible or zero. That's very important over here. So what do we take the time of collision to be? How long the particle takes to travel from 1 to 2 to 3. So this entire journey is the time of collision. Yeah,
So it collides with the wall at 2, right? So
yeah.
isn't it 1 to 2? And it's
So you,
exerting the force at 2. Isn't it?
yeah. So I mean, technically speaking, the time of collision should be just how long the particle was in contact with 2 at 2,
Yeah, yeah.
right? Yeah. So I will answer that over here when answering this. I'll answer that question that why do we make this assumption? Okay, this entire explanation answers your question. But before there, what in reality over here for the derivation, what do we actually do? We consider the entire path of the particle. Entire path of the particle we consider from going from 1 to 2 to back to 1. And I'm going to show the step and then explain why it is considered. So the time of collision we consider as total distance covered by the speed of the particle. What is the total distance covered between the walls? L plus L. So 2L divided by the speed of the particle, which is we considered c, because v is equals to d by t, and t is simply distance by velocity. Clear? So this is the time of collision, 2L by c. Now to answer your question, why on earth do we do this? And one of the most confusing things that there is in the entire A-level chapter, because there's a
Wait,
direct
sir.
answer. Yeah.
The speed is constant always.
Yes, I mean, speed is constant. Yes,
Like in
velocity is
the
not. Velocity changes.
kinetic
Yeah.
theory, like we assume that they have random speed, right?
hmm There's a
So
distribution of speed
is
amongst
this
all particles. Yes.
is this random speed constant or
So if I'm modeling this entire derivation with respect to one particle, and granted it went through no collision, this is the assumption I'm making. It while reaching the wall, there is no collision taking place for the particle. So it has the same speed while arriving. Okay. So
or
no change in speed takes place. Only when the change in momentum takes place, its velocity changes, that is opposite direction, hence the change in momentum. But yes, speed stays the same. That is the assumption we're taking over here. Okay, great. Now coming back, why is this time considered? Why do we take the entire journey? Valid question, good question. I took 1 week to understand this, and even then, I wasn't satisfied. The thing is, uh, think of it logically. Take a step back. First problem we have is time of collision is negligible. When you have force is equals to change in momentum by time, and your change in momentum is some significant real value, and your time is, let's say, I'll give you a perspective. Let's say change in momentum is 0.02, and your time of collision is 0.0000000000002. You get the idea. What will force be? Almost infinity. Okay, really large. That is not what happens in real life. That is not what happens in real life. Okay, it's not an infinite amount of force applied on the wall of the container. So since the time is negligible over there, considering that A is not possible. First. Second is we average that force out throughout the journey. What does that mean? I'll explain. Basically, during this entire journey of time, 2L by C, how many collisions take place? For this one particle being modeled, how many collisions take place? One collision. So through that entire journey of the particle, one collision has taken place. Now, it is not that the force on the wall is, let's say, if I model it with respect to time, force over here, the entire journey of 2L, the entire journey of length has been zero, and all of a sudden there's a spike in force, and all of a sudden the force decreases to zero. This is not something that happens in real life. The force on the wall is pretty much constant, not entirely constant. It will be something like this. The force on the wall is pretty much constant. But why is it that when I do this derivation, and when I have the particle colliding with the wall, all of a sudden only when the collision taking place, there's a force applied. Rest of the time, there is no force. Is this possible? No. So we average whatever force is applied during the collision, we average it out through the journey. Basically, whatever force is applied on the wall during the collision, we don't know that. We average that out through the journey of going from 1 to 2 to 2 to 3, because that is the only way it makes sense. So we take the force, we take the change in momentum and say this change in momentum is happening throughout the journey of the particle. And the reason it makes sense is the force is same throughout the journey. It is not that if it takes 2 seconds for the particle to go from 1 to 2 and 2 seconds to go from 2 to 3, during those 2 seconds there's zero force, and right at the middle after 2 seconds instantaneously there's a spike in force. That is not what happens. So in reality,
Okay, sir,
that
if
force
it
is
takes
averaged out. Yeah.
um 2 seconds to go from 1 to 2, will it also take 2 seconds to go from 2 to 3?
Yes. In this assumption, yes. In this model assumption, yes.
Oh,
Okay. Because we don't have any other particle in this example. So in essence, the force on the wall, or that change in momentum on the wall, that impulse on the wall, is averaged out for the entire journey of the particle. That is how we find the force on the wall. Do we understand why we're averaging it out? Because it is not realistically, physically possible that only for one instantaneous point there's a spike in force, and for the rest of the time of the journey, it's zero force on the wall. Okay, this is why we make this assumption that the time of collision is the entire time of the particle's journey from point A to B and B to A. So that is why we consider this distance. And we get the time, and this time is the entire journey. So this is the force ultimately. Any confusion till this point?
no.
Great.
Sir, could
So
I see
now,
that?
yeah, you want to screenshot this? Let me know if I need to go up.
Is it be possible to zoom a bit more?
Zoom in or zoom out?
Zoom in.
Okay, on which part? The reasoning part or the
Yeah,
step part?
reading. Yeah.
Okay, great. They won't ask you this, by the way. If they do ask you, you just say that the time of collision is very negligible, so we consider the entire time of the journey. That simple two sentences you write if they ask you, but otherwise they are not going to ask you this in general.
Okay.
Okay. Now step 4. Did we find out the force? Yes. It is change in momentum by change in time. What is the time we found out? Del T is 2L by C. Okay, so we provide this del T, substitute this del T as 2L by C. Great. So now we can cut off the 2's and I'm left with mc square by L. This is L, by the way. Okay, so ultimately this is the force exerted on one wall by one particle. So if I model a box with one particle inside, the force exerted on the wall constantly would be mc squared by L, where c is the velocity of the particle, m is the mass of the particle, L is the length of the box of one side. Okay, so this is ultimately the force exerted on one of the wall by one particle. How do we find the total pressure? How do we find the total pressure by one particle on one wall? The pressure would be now, whatever the force is, you know the pressure to be force by area. Is that clear? So the pressure would simply be whatever the force it is divided by the area. What is the area? If you have a box over here, what is the area? L square is the area. Okay, so I divide force divided by area and I get the pressure. Great. So what is the pressure by one particle? mc squared by L cube. Now, is it that in real life we have only one particle inside? Nope. Nope. We have n number of particles. How many particles? N number of particles. Doesn't matter what it is. Could be any amount of, but n number of particles, let's say. And that results in multiplying this pressure with n number of particles. So it's simply n times mc squared by L cube. Okay. Now all of these n particles exert the same average force that we found out. Sorry, average pressure that we found out. So it's simply n times this average pressure. Okay. Okay. So initially, what did we do? We considered the time of collision to be the entire journey. As a result, we averaged the force out through the journey. And that average force resulted in an average pressure, P, of one particle. And that average pressure by one particle, I multiplied with n number of particles to get the total pressure on one of the walls. Okay, this is how we get the pressure. Now, this is not done. This is only the beginning. This is only the beginning. This is not done. So, now we have ultimately, if we are clear on this,
Hey, could
pressure,
you explain this again?
which
So
one?
we are assuming particle by particle, right?
Yeah,
So using the F by A formula, we find this.
yeah. So we find first the force by one particle. Is this part clear?
Yeah.
F by. Now, what we do is we say, okay, my box doesn't just have one particle, it has n number of particles, multiple other particles. Let's
Yeah.
say 6 million particles. Okay,
Yep.
so I simply multiply this pressure of one particle with n number of particles, in my case, 6 billion particles. So what does that do? It increases the pressure inside the box. Remember, PV is equals to nRT
Yeah.
or PV is equals to nKT. If I increase the number of particles, what do you think would happen to pressure? Pressure increases, right?
Yeah.
Exactly. So that is what's happening. I simply multiply this pressure of one particle with the n number of particles because I now included in my box 6 billion particles. So that is my number of particles. So this is the total force on one of the wall due to n number of particles. Clear?
Yep.
Great. Now, what do I ultimately get? Same formula, nmc square by L cube. What do you see as the difference over here? Like this is ultimately my pressure formula. This is not the end formula. Don't get confused. But this is right now the pressure formula I have. What's the difference over here?
We're taking average of C squared.
Yes. So what you see over here is mean square speed. What does this mean? And I'll explain this to you guys. So this sign basically means the average speed square or the mean square speed. Let's discuss what this mean square speed really means. This is the only difference between these two formulas. What we found out and what ultimately I'm writing as the formula of pressure, there's just one difference, and that is mean square speed. What does that mean? What does the mean square speed mean? Let's say we are working with a distribution of particles inside, all of them with random speeds. Let's say speed A, speed B, speed C, right? And what we do is we square those speeds out and divide by 3 to get the average speed square. Okay? Simple till this point. Now what happens is we can root this value to get the root mean square. So what did we do till this point? So let's say A is 2 meter per second, B is let's say 2.1 meter per second, then C is 1.9 meter per second,
Wait,
square,
sir,
square,
aren't
yeah,
all the particles moving with like similar speed? I mean, same speed?
similar speed. Not same speed when in real life, all the particles will have some amount of speed distribution in them. So some will have like this little variation that you see over here. Okay, so there's a bit of a difference between speed, but when you average them out, which we are doing, we get the mean square speed. So the mean of these values squared is the average that we consider. And that is an accurate assumption because we're simply averaging all the discrepancies out and getting the average speed. Okay,
Yeah. So
so
would
that
this
we
give
use
us C square or just C? Like,
this one. This
yeah.
will give you C square, average C square value. Okay, now, so what do you do if I just want the C? Average velocity. This is giving me average velocity squared. But I want just the velocity. What is the average velocity? What do? We will simply take a root of this value. So whatever this value comes out to be, right? Whatever this value comes out to be, let's say the value comes out to be d square, right? Whatever the value comes out to be, I take a root of that value, whatever we found out over there. I take a root of that value and say this is my mean speed value or the root mean square value. So the root of the mean square value. This is my mean square value. And I take a root of that to get root mean square. Don't get confused with the wording. These are new words, may be confusing. But basically, you're taking a root of the mean square value. Okay, it's just that. Now, why do we do this? You will ask me, my friend. Well, when I average all the speeds out, all the velocity out, what do we have? A particle A can travel in this direction in the box. Okay, this is in the negative direction. If I model leftwards, it's negative. It can travel in this direction. It can travel in this direction, in this direction. All the velocities are different, even if the speeds are same. But speeds are also not same in reality. Speeds are also different. Velocities also different. So one has, let's
Sir,
say, a minus. Yeah,
when
yeah.
we use the speeds when finding the mean C square, do they all have to be in the same axis or?
Okay, so that conversation of different axes comes over here.
All right.
Okay. So we do consider that what you're saying. That is why you will see the 1/3 constant in front of the formula. So as I told you, this is not the ultimate formula of pressure. And what you said is the reason for it. That do we just consider one axis? No, we don't. We consider all the other axes and we get the ultimate pressure formula. This is just, as I told you, sort of the middle of the book. We are still left with the end of the book. Now look, for the Ooh, where was I? Okay, so why do we take the mean square, root mean square? Can't I just average all the speeds out? Like typically what we do, if I have different velocities, I'll just average the velocities. Why do I need to square them and then take the root? What's the point of that? You will see this in statistics. If all of you guys are doing S1 right now, you will see this over there as well. Okay, you'll study this over there as well. Basically, look, when I have multiple velocities over here, one may be negative, one may be positive. It's valid, it's possible. They can be traveling in different directions with different amounts of speed. So what we do, we basically square those values out, and what we get are positive values, positive squared values. Then we divide them by however many values there are or however many atoms there are, then take a root of them. So first I find out the average squared value, then I take a root of that average squared value. And ultimately I get the root mean square value. Okay, so this is why RMS or root mean square is used to get rid of the negative values. And I get a sort of an accurate average of all the particles speed. Okay, that's why we use root mean square. Which one is root mean square over here? This. Don't get confused. Which one is speed square value, mean square value? This. C square. That is not 3. Okay. Which one is root mean square? This one. Which one is speed square value, mean speed square value? This one. Don't get confused. Okay. Here, RMS may also be written to make your life easier. Okay. Know the distinction between the two. Great. Now, ultimately, are we on page with this formula? Only difference is I converted the speed to root mean square speed. And we told you guys why we do that. Okay. Now, if we all understand and are on page with this pressure formula, we do the next thing, which is we consider 3D space, as you said right now. No, the particles don't just travel in one direction, they can travel in all the 3 dimensions. So, okay, where is the box? I have a box over here. Okay, I'll just draw another one. So look, that ultimately, when you have a box filled with particles, the objects can go up, I mean, particles can go up, down the lane, or even right. There are 3 possible directions that the object, or sorry, the particle can travel in. So in reality, all the molecules do not just travel in one direction, rather, they can travel in all the 3 directions, X, Y, and Z. The speed of the possible split in all 3 directions are equally done. That means whatever the true speed of the particle is, let's say, to make it a bit more simple, if a particle over here, right, is traveling in this direction or in this direction, there is a X component, there's a Z component, and there's a Y component. So this velocity C has a component in the X direction, has a component in the Z direction, has a component in the Y direction. Agreed? So this particle, my friend, that is traveling around in random direction has has components in all of the X, Y, and Z direction. Can we agree on that? Now, yes, the particle can travel just in Y, the particle can travel just in X, the particle can travel just in Z as well. but there will be an equal distribution of that. If I have so many particles inside, it's a 6 million, 6 trillion particles inside, doesn't matter. The distribution of that would be equal between all the three directions if they are only traveling in one direction. And the particles which are not traveling in one direction, they have components in all of z, x, and y. And when you consider all the particles, it turns out to be very fascinatingly that on average, or if you add up all the components out of all the particles, there is equal amount of speed in z direction, equal amount of speed in x direction, equal amount of speed in y direction. Can we agree on that? Yeah?
Wait,
Yeah.
we're saying that the component has equal amount of speeds in each direction. Like the components are equal. Is that what?
Not for one particle. So if there is just one part, if you're talking about one particle, it can have more component in the y direction, less in the x, and even lesser in the z.
Yeah.
Okay, for example, like this one. But when I have another particle to be considered, it will have more in the, let's say, x direction, less or least in the y direction, and more on the z direction. Now, when
So
you
the
do this,
total system will have equal amounts in all. Uh,
exactly. When you
okay.
consider the total system, it is equal speed in all of the components. Yeah, individually, each particle can have more in either of x, y, and z.
But it will be
But when you,
balanced. Yeah.
yes, exactly. Correct, correct. So when you consider the total system, it is equal on all of those directions. So what I say, I can now use something very interesting in maths. Like technically, the speeds are split in all three directions for the total system. Now, using the Pythagoras theorem, I do something very interesting over here. I say that the resultant speed, whatever the resultant speed is, has a component in the x direction, has a component in the y direction, has a component in the z direction.
So
Whatever my speed, yeah.
I don't understand. I didn't understand what you meant by they have all the same speed in the different components. I didn't understand that part.
So basically, when I have a box over here, any system over here, and I have particles, the particles can travel, the particle can travel if I take this as the x direction, if I take this as the z direction, let's say, and if I take this as the y direction. If the particle's direction is, let's say, over here, so it has pretty much zero speed in the z direction. It has, let's say, 50% of its speed in the x direction and 50% in the y direction. Okay, so this particle's components are in x and y direction mostly. No amount of its speed is in the z direction. Now, if I take another particle over here, let's say it's traveling in this direction. Okay, it's traveling in this direction. Most of its component is in the z direction, somewhat in the x direction, and very little in the y direction. So what I'm showing to you over here is multiple particles. If you consider a lot of particles, all of those particles will have different amounts of speed in x, y, and z. Some will probably not even have any speed in the y direction, any speed in the x direction, any speed in the z direction. But when you average all of them out, what you see is for the total system, all the particles, equal amount of speed is in z, equal amount is in x, equal amount is in y. And if that statement is a bit confusing to you, basically, if I have with respect to like three particles, A, B, and C, if it has 2 meter per second of speed in x direction, y, and z, let's say. If A has 2 meters per second speed in, let's say, x direction, 3 in y, and let's say 0 in z. And B has, let's say, 0 in x direction, 0 speed in x direction, 2 in y, and 3 in z. And for C, it has a zero component or zero speed in the y direction. It has 3 meters per second in the x direction and 2 meters per second in the z direction. Are you getting where I'm getting with this? So when you take
Yeah.
multiple speeds, all of them take the total over here. In the x direction, what is the total speed? 5. In the y direction, what is the total speed of the system? 5. In the z direction, what is the total speed of the system? 5, right? So
Yes.
this is what I mean. Of the total system, when you take a gazillion particles inside, when you add all of their components, it's equal in x, equal in y, equal in z. Clear?
Yes, sir. Thanks.
Great. No worries. So ultimately, I can say that if I take a random particle over here, its speed is comprised of x component, y component, and z component, right? So similar to the Pythagoras theorem that you have for like two dimension, what is this speed? What is this component? If this is y, this is x, and this is, let's say, a. My a square is equals to y square plus x square, right? So if this is the same as y, right? So x square plus y square is equals to a square. This is what you guys know from before, right? So I'm just using that idea, but in three dimension. And it's just so turns out to be that it works in any number of dimension. So if I have four dimensions, let's say CF, right? I don't know what the fourth dimension is, but if I have four dimension, the net speed or the net value or the total value, resultant value is simply the square of all the dimension. So it doesn't matter how many dimensions you have, this Pythagoras theorem always works for all dimension. Okay, you guys are used to using this with two dimension, but it also works in three dimension. So if it has some component in x, some component in y, and some in z, take the square of all those components, and that is equal to the resultant speed squared. Okay, so similar to over here, if I have a particle over here going over here, right? This is the particle, this is the velocity, this is my x direction, and this is my y direction. So this velocity has a component in the z direction, in y, and also x. And if I square all of these components out, I get the velocity squared value. That is all I'm saying over here. Now, since there are equal chances of the ball moving in each direction, we can say, I just showed you guys how it's equal, that of the total system, speed in each of the directions are equal. So essentially now I can say the speed square in x direction is equal to speed square in y direction is equals to speed square in z direction. I can see this. Okay. So now the resultant speed is simply 3 times the speed square in any direction. How did I come to this? If you're confused about this, all I'm saying, my friend, is if Cx is equal to Cy is equals to Cz, can I simply write this equation as C square is equals to Cx square plus Cx square plus Cz square? Or I can also say it's equal to Cz square plus Cz square plus Cz square. Can I not say this? I can, because all of the components are equal, right? So if I can say this, I can also say C square is equals to simply 3 times Cx square. Can I not say this? Yes, I can. Because all of the components are equal. So if I just convert with respect to any one of the direction, well, it's simple. I just get I just get my net speed squared or resultant speed square is 3 times the speed square in any direction, x, y, or z. Does not matter because all of those are equal. Now, if I have that, the speed square in any one direction is simply equal to 1/3 of the resultant speed square. So I'm simply taking the 3 on the other side or dividing by 3 on either side, and I am left with, for any one direction, what is the speed? What is the resultant speed in any one direction? 1/3 of the resultant speed. Any question?
Wait, what? Isn't it equal to each other? So how is it 1/3 now?
No, 1/3 of the resultant speed, not of
Oh,
any one direction.
oh, okay,
So
okay.
whatever the resultant speed is, if this is my resultant speed, and these are the components, y, x, not y, sorry, x, z, x, and y. If this is my velocity, right, and I take multiple velocities, on average of the total system, the velocity in the z component is 1/3 whatever the sum of all these magnitudes are,
Yeah. Okay, I get it.
right? And 1/3 in the x direction, 1/3 in the y direction. So I'm talking about that the magnitude of the speed squared is 1/3 in each of those directions of the resultant speed. That is all I'm saying.
Yeah.
Okay, great. So
So
now,
in our questions, we
ultimately,
only
yeah,
consider three directions: the x-axis, the y-axis, and z.
yes. I mean, in physical world, we will just consider the three directions. Yes, yeah. So now, what happens is, what is the pressure applied on one wall? There is three possible direction, right? How am I drawing this? Wait, I'm doing something so wrong over here. I don't even know what I'm doing. Just stick with this. Look, there are three possible walls in three different directions. One is up, the wall above. One is the wall on the side, the wall on the front. So one in the, let's say, z direction, right? One in the x direction, let's say, and let's call this at the y. Clear? So there are three possible walls over here. And same, I mean, a cube has 6 sides, but the other sides are simply negative z, negative x, and negative y. So let's go on with that idea. But there are three possible direction of walls over here. One in the z direction, one in the y, one in the x. Right? So basically what I'm saying is, if I'm considering one wall over here, one wall over there, what is the pressure on that one wall? It is simply 1/3 of nmc square by L cube. Did we find out P is equals to nm? Did we find this out above? Yes, right? We figured this formula out above. All I've added over here is 1/3. Why? Because in any one direction, for any one wall, in any one direction, the pressure exerted will be 1/3 of this pressure. Because this pressure is defined by the total resultant speed squared. But that total resultant speed square is simply distributed in three directions, right? There are three directions that the total speed square is distributed in: x, y, and z. So I take 1/3 of that pressure. So 1/3 of that pressure exerts on wall z, x, sorry, z, y, and x.
So this is
Okay.
the pressure in one axis.
Yeah, pressure in one axis.
And it's equal in all axes, right? It's the same.
Yeah, it's the same. So all of the walls will have a pressure of 1 by 3 nmc square by L cube. Okay. Now, I can further simplify this. Now we're towards the end of the derivation. Now we can say that if I take L cube on the other side, PV, L cube is what? Volume, right? PV is equals to 1 by 3 nmc square. The other thing I can do is something interesting. This is one formula. This is one way to represent the formula. The other way to represent this formula is I can take this portion and I can simplify this portion. What can I say over here? What is N? How can I simplify this? What is M? N is the number of particles. What is M? The mass of those particles, each of the particle. And L is the volume that is available to them or they're occupying. So N times M is the total mass of the particles, all the particles. So basically M, large M, total mass of all the gaseous particles inside, divided by L cube, the space this total mass is occupying. What does this give me? Mass by volume. What is that? Density. This gives me the density of gas inside. Okay? I get the density of the gas inside. So the density of the gas I can substitute over here. And that is all I do. 1 by 3, instead of Nm by L cube, I have density of gas times mean square speed. And this, my friend, is something that you're going to use as well because they're going to give you the density of gas in a box. And they'll ask you, what is the pressure exerted? Or if they give you the pressure and the density, they'll ask you, what is the mean square speed of the particles? Okay, great. If you understand that, you've done a good job till now. Last thing is very, very, very important over here. And that last thing says, what is the average kinetic energy of one particle? Did I, towards the beginning, yesterday especially, teach you guys this? That kinetic energy of a particle is related to its temperature. And the temperature of the particle is related to its kinetic energy. Vice versa. Right? And this is the formula I want to derive. That temperature and kinetic energy is related. And we derive that using the kinetic gas theory. Same formula. Everything that we discussed till now leads up to this point. And I would say this is a very important discovery. We understand thermodynamics, a lot of its properties, a lot of the things that we know today due to thermodynamics is because of this relation between temperature, kinetic energy, and internal energy. All of these are very, very important. Okay. Now, every particle has a certain kinetic energy, except for when it is at 0 Kelvin or absolute zero, where there's no kinetic energy. The particles have zero energy. So, except for that, all the particles have some amount of kinetic energy. And this kinetic energy presents itself in mainly two forms: translational kinetic energy, so moving from one place to another, and rotational kinetic energy, so rotating about one point. These are the two sorts of kinetic energy you can have, typically speaking. So, the translational kinetic energy can be seen for both monoatomic and diatomic molecules. So, if I have a monoatomic molecule or atom over here, and I have a diatomic molecule which is connected by a bond. Both of these can translate from one position to another, and that is translational kinetic energy. So the energy to move from one point to another, that is one form of kinetic energy. The other is rotational kinetic energy. And this is only possible when you have a diatomic molecule, because this can create a moment about a point and this can rotate. For this, there is no rotational kinetic energy, that is a monoatomic molecule. So a diatomic molecule can rotate around and have a rotational kinetic energy, while a monoatomic molecule cannot. Clear? Great. Now, this kinetic energy can actually be derived very interestingly using the pressure formulas that we figured out. One is PV is equals to NKT. The other one is PV is equals to 1 by 3 NMC square. Where does this come from? We just derived it. And you saw this form of the formula. You guys recognize this? We just derived this right now. So we're going to use this and this. So I've basically taken V on the other side or multiplied by V on either side to get this format. So what I am setting as equal is PV and PV. So I'm saying NKT is equal to 1 by 3 NMC square. And I can cancel the number of particles on either side. And I'm left with 3 KT. I basically multiplied by 3 on either side. And I'm left with 3 KT is equals to MC square. Now look. Does this look very similar to something, my friend? What is the formula for kinetic energy? Half mv square. Do I have mv square over here? Yeah, you do. You have this is velocity, mean square velocity, and this is also square velocity. Can I do something over here? Can I bring half into the equation? Can I multiply with half on either side? Yes, I can. There's no problem. So what I do is I multiply by half. What I'm getting is 3 by 2 kt is equals to half m mean square speed. This is what? Ke, kinetic energy. So kinetic energy is actually equal to 3 by 2 kt. That is it. This is your relationship. Kinetic energy is equal to 3 by 2 kt. And if you want me to break down the Boltzmann constant, I'll do that for you. 3 by 2 times reaction of gas constant divided by Avogadro's constant times thermodynamic temperature. So what is kinetic energy essentially related to? Just the temperature. And what is temperature related to? Just the kinetic energy. This is the ultimate proof. And this is pretty much one of the most important things you will study in physics, at least as of now. Do we get this?
Yes.
Great. And by the way, this is not the kinetic energy of a system. This is the kinetic energy of one particle. What do you do if you have a box and it has n particles and they're telling you the temperature of the box or the particles is 320 Kelvin? How do you find out the kinetic energy of all the particles inside of the gas? You say Ke is equals to n times 3 by 2 kT. Okay. So what do you have? You have the number of particles, which the question, let's say, gives you, times 3 by 2, which is a constant, times K, which is also a constant, and given in your formula sheet, and times the temperature, which is 320 Kelvin. So this kinetic energy is what? Total kinetic energy of the system. Now you have something so valuable. You can find out total kinetic energy of a system simply by this formula. Clear? Any confusion till this point?
No.
Great. So look at this, that the kinetic energy is directly proportional to the temperature, thermodynamic temperature. So kinetic energy is only affected by temperature. Keep that in mind. One of the most important thing you guys will need to answer questions, qualitative ones. Now, ideal gas is done, which was very long, but yeah. Now I'm
There,
gonna give you, yeah,
any of those formulas that we found out, will we be asked on how to derive them?
yes, you will. That's why it's important.
Okay.
You will be asked for derivation. That's one of the most important chapters for derivation. Now, uh, thermodynamics. I consider, I mean, I in general just classify the question as thermal physics. So you will see on YouTube often. I have question on thermal physics, hard question compilations, and for that, thermal physics. I consider thermal physics to consist of temperature topic. So question for temperature, ideal gas, and thermodynamics. This one. Hard questions from all of this I compile into thermal physics chapter, and you'll find a few videos on it. And it's essentially interchangeable. The reason I'm saying this, when you do the papers, all of these things sort of come bushed up together, and it's interchangeable topics. Uh, so it may be that if they give two of these topics, the other one won't be given. So they're just taken as a whole when questions are asked. Now, over here, when studying thermodynamics, you pretty much, one of the core idea is understanding the internal energy. What is internal energy? If I have a box, if I have a system, what is the internal energy of the particles? Total energy of the particle. Total energy. And that total energy is a sum of kinetic energy and potential energy of the particles. There is no other form of energy. Whoop. So there is no other form of energy available to the particles. There is only kinetic energy and potential energy, simplified form. Okay, you can say if I provide heat, then it's simply that if the temperature is raised, then the kinetic energy raises. So practically speaking, it is simply kinetic energy and potential energy. If you can say, okay, there's electric energy as well, but that even that is simply movement of charge, or you're pushing the charge apart and you're storing potential energy. All of those things distill down into kinetic and potential energy. Okay, so essentially, sum of kinetic and potential energy gives you the internal energy. But in case of ideal gases, what did we consider the potential energy to be? Zero. Okay. We consider for ideal gases and thermodynamics. We over here we will only talk about gases, no other substance, not liquid, not solid. We only talk about gases. So for ideal gases, potential energy is what? Zero. So ultimately, this is null. So the internal energy practically is only comprised of the kinetic energy of the particles.
Sir,
That
why
is
is
it.
the potential energy zero again?
We basically, when today we started off with the assumptions, we said we assume potential energy to be zero, and the reason for that is for the particles, since they're really far apart, gaseous particles, and the mass is low, their potential energy is negligible. If you want proof of that, did you study gravitation? You have to relate it to
Sir,
that.
is this
So
potential energy like gravitational potential energy or?
yes. So like gravitational potential energy or electric potential energy, everything considered in general, all of those cases, potential energy distills down to this relationship, that how far the particles are. If the particles are really far apart, then the potential energy is low. Clear? So in that, over here, we are considering if these are not charges, yeah, sure. We are only going to consider gravitational potential energy. And yes, the potential energy over here essentially means the GPE. So
Did you say the GP of each particle is zero or like the system? Oh,
of each particle, you have to consider it to be zero, yes.
uh,
And of the system is zero as well as a result. So over here, what is the mass? Over here, if I take masses are really small, right? And the separation is really large. What does this lead to? Really small. Okay. And negligible. Because this is by proof of the formula. And when your mass is really low, separation is really large, the potential energy between the particles, really small, negligible. Clear? So that is why we consider P to be zero.
yeah.
Now, so the internal energy is basically the indication of its kinetic energy. Okay, or kinetic energy is an indication of its internal energy for ideal gases, just for ideal gases. If I'm talking about solids, liquids, different case, different case, different case. You then have to consider what? Potential energy as well. So now, the internal energy, it turns out to be that it can only be affected by doing work on it. That is, if I have a piston over here and I, let's say, do some work on the gas, there's gas inside, and I decrease the volume, I work on the volume, sorry, I work on the gas, I do work done, and that is one way to increase the internal energy of the particles. Clear? That is one way to increase the internal energy of the particles. We are providing less space, the more collisions take place, they gain the velocity. So kinetic, in some essence, kinetic energy increases, temperature also increases, hence internal energy increases. So one way is doing work on the gas, reducing the space. The other way to raise internal energy is adding heat to the system. So if I heat up the system, increase the temperature, again, internal energy increases. So ultimately, this is the equation. Del U, change in internal energy, is equal to the heat supplied. Mind you, this is not the internal energy of the system. This is not. This is not the internal energy of the system. This is the change in internal energy. Don't get confused over here. If they ask you what is the internal energy of the system, that's not what they'll ask you. They'll ask you what is the change in internal energy of the system. The change in internal energy is given by the heat supplied plus the work done on the gas. If it's by the gas, if volume, look, if the volume is reducing, work is done on the gas and this remains positive. If the volume is increasing, the formula becomes this, because work is done by the gas. Okay, so gas loses energy. So these are the two forms you have. In both cases, it's heat supplied. So the change in internal energy is the sum of heat supplied plus work done on the gas. Okay, clear? This is the formula of change in internal energy. And the very important part that you guys need to understand over here, internal energy never changes if the temperature doesn't change. Doesn't matter what happens to work done, doesn't matter what happens to heat supplied. Like, look, if I tell you that work is being done on the system, but temperature is constant, then you have to understand that probably heat is being emitted from the system. If my temperature is constant, that means my internal energy doesn't change. Del U is zero. So if the question tells you, I'm doing work on the system, but temperature is constant, what is happening to the heat of the system? Heat is exiting the system. Has to. For the internal energy to remain constant, the heat has to get released from the system if the temperature is constant. So the indication is over here, del U is proportional to temperature. If temperature doesn't change, internal energy will never change. Keep that in mind. Why? Temperature is related to kinetic energy. So if the kinetic energy doesn't change, internal energy will never change. What is internal energy comprised of? Ke and Pe. Do we consider potential energy? No. So internal energy for ideal gases only related to kinetic energy. And what is an indication of kinetic energy? The temperature. So if the temperature never changes, internal energy also never changes. This is the golden thumb rule that will save your life when solving the questions. Trust me on this, and I'll show you how.
All right, sir. When we say heat, right, we mean thermal energy, right?
Thermal energy, yes.
Yeah, and we say thermal energy is equals to potential energy plus kinetic energy.
No.
No?
Thermal energy is simply the heat supply to the system. or taken away from the system. Any amount of heat energy in the system is thermal energy. Now you can consider it in terms of kinetic energy provided as well. That is equal to thermal energy. You can say. What is your question? Is it equal to? Is this equal to
Yeah. Yeah.
internal energy?
Is thermal energy equals to kinetic plus potential? No. I
Is no, no.
in
Thermal
one
energy
word.
is simply you could say kinetic energy.
Oh, all
I mean,
right.
it's not really. Both are different definitions, but yeah, you could say that if basically what I was explaining over here is if the temperature, if let's say work is done on the system, so my work done is increasing, but temperature is constant. What happens to the change in internal energy? Change in internal energy is zero. What? How did I understand that? Temperature is constant, but my work done is increasing. So what happens really is thermal energy has to exit the system to keep the temperature constant. So it's basically releasing all that kinetic energy of the system to outside by heat transfer. Are you getting the idea?
Yeah, but in Google or in some notes, I saw that they said thermal energy is equals to kinetic plus potential. So I was wondering here, we said that it does not depend on potential energy, right?
Yeah.
But if it depends on heat, which we say is thermal energy, then if we break thermal energy down into kinetic and potential, then we see it does
Uh,
depend on.
thermal, I don't know if you can classify thermal energy as KE plus PE. I'm not really sure about this. This is what where I'm getting confused. Well, at least for this syllabus, would they classify thermal energy as KE plus P? I'm not really sure on that.
Oh,
Like the
okay.
proper definition would be that internal energy is comprised of the heat supplied. Sorry, change in internal energy is equal to the heat supplied plus the work done on the system. That is the proper definition, I would say, right? And internal energy comprises of kinetic and potential energy. And kinetic energy is an indication of what? Uh, the thermal energy of the system or the temperature of the system.
Yeah.
So you can say that, yeah, technically that thermal energy is kinetic energy over here. And that is the only thing that is determining the internal energy. But you can't just relate heat transfer to the system as, the total thermal energy, right?
Yeah.
So
So
this
basically in
this
this
is telling.
syllabus, we don't have this, like this not, right?
No, I haven't really seen this description. No.
Okay.
Okay, fair enough. So, this is the change in internal energy. Is the change in internal energy clear?
Yes.
Okay. So, change in internal energy only happens when we supply the heat or do work done on the system. Now, if we take that idea on, what is this? I've explained this. Fair enough. Now, I showed you right now before in the last PDF that change in internal energy is only related by the temperature. Okay. Okay. And since how does this come up about to be? Basically, instead of change in internal energy, you saw Ke is equals to 3 by 2 kT, right? So basically, since internal energy is simply kinetic energy plus Pe, but there is no potential energy. So internal energy is simply kinetic energy. So change in internal energy is change in what? Kinetic energy. So change in kinetic energy or change in internal energy is equals to 3 by 2 kT. And hence my internal energy is related to temperature only. Fair enough? Okay. So now, if you are clear with all of that idea, I'm going to show you one question and end this class today. Remember, this statement is going to help you. For ideal gases, changes in temperature is the only factor determining the internal energy. Okay. Now look at this. I'll actually show you two questions, I guess. If an object, if a system of gas goes from state A where it has a certain volume, pressure, and temperature. And the temperature increases where the volume has decreased, pressure has increased, and temperature has increased. Now it goes from B to C again, where pressure remained the same, volume, sorry, volume remained the same, pressure has decreased, temperature has decreased. Now from C to A, if it goes back again to this same state, what is the change in internal energy? What is the change in internal energy? Give me a guess.
No change.
No change. Why? The temperature remains same. Eh, this is the sole thing. Temperature remains same means no change in internal energy. So through the cycle, doesn't matter what shenanigan it does, the internal energy remains the same. I don't care what heat was supplied. I don't care what work was done. Temperature doesn't change means no change in internal energy. Last question I want to show you guys. Not this. I'll cover the work done part a bit later. This, and this. All of this I've actually discussed with you guys, but I have shown over here extensively. But I want to show you this question. Notice B. This is a good question again, and rest we will continue next class. You're pretty much done with thermal physics. Just one thing left, a little thing left. But I want to show you guys this question. So look, the state of an ideal gas is continuously changed according to the cycle A, B, C, D, A. Goes from A to B, C, then D, then A again. They're asking you complete this table. For A to B, what is the change in internal energy? What is the change in internal energy? What do you think? So change it from A to B, my pressure constant, volume decreases. You tell me what happens. What happens to internal energy?
Uh, Increases
Why?
because volume on a volume decreased. Well,
Yeah.
temperature decreases
How do you know that temperature decreases?
because
Because
they are
volume decreases.
proportional.
Mhm. Well, if I decrease the volume, shouldn't the temperature increase because I'm, well, could be increasing the pressure, but actually it's the pressure is constant. But no, you have to use the formula over here, some sort of formula over here. A to B. So pressure is constant, V is decreasing. So if you use del U is equals to heat supplied plus work done, I'm doing work on the system. Shouldn't the internal energy increase?
Yeah.
So what do you think happens? Last guess. Give me a last guess. Think and give me a last guess.
Um. Well, since they're inversely proportional to each other, temperature and volume.
No,
Um.
they're not. So that was when we are talking about ideal gases and we were keeping something constant. Yeah, go ahead. I want to see the trail of thought. It could be something. Yeah, go ahead.
Yeah. So I thought if they were inversely proportional, then since volume decreases, temperature will increase.
Okay. Temperature will increase.
Yeah.
And so the internal energy will
Increase.
great. Fair enough. So that is an answer. Now look. PV is equals to nRT. Okay. The answer is decrease. And why am I showing this question to you? What you just did, a lot of students have done this. A lot of students have done this. This is why I'm showing this question. Why? Because look, when you're working with that idea, PV is equals to nRT, you cannot just work with one of the relation and try to find out what's happening to the entire system. When you gave me that relationship between V and T, right? Uh, what was wrong over there is you said V is inversely proportional to T. First thing, that is wrong. If you just went on with that idea, that could have been correct actually. That is not entirely wrong. So, which is why I stopped myself and wanted to hear from you. But this relationship is wrong. V is proportional to T. Okay. Do we remember this? Do we remember that volume is proportional to T in that?
Yeah.
Yeah. So this is where the trail of thought was a bit wrong, but you were actually onto something, which is why I realized that and I stopped myself. But yes, over here, what essentially happens is look at the relationship between temperature and PV. P is what? Constant. Okay, P is constant. And if my volume is essentially decreasing, notice volume is decreasing, my temperature will decrease. So as a product, PV, it is decreasing. P is constant, but volume is decreasing. So temperature is decreasing, right? So that is why since temperature decreases, internal energy decreases. So internal energy decreases. Now your trail of thought was actually good, which is why I will compliment you. But what people usually do wrong with their trail of thought is actually this. They go to this formula, which I just taught to you guys, which is Q plus work done. And they say, well, work is done on the system, so internal energy must increase. And they give that internal energy increases. But brother, what you don't know, and sisters, what you don't know is what is happening to the heat. You don't know what's happening to the heat. You don't know if heat is emitting in the system, right? So you can't just say that work is done on the system, hence internal energy increases. Heat probably is emitting way much more from the system, which is why ultimately the internal energy decreases. So the right way to think about is what you were doing, Owen, that you consider the PV is equals to nRT equation and said, okay, if P is constant and volume is decreasing, temperature should also decrease, hence internal energy should also decrease. Do we get this?
Yes.
Great. Perfect. What happens B to C to internal energy?
The volume is constant. The pressure has increased. Uh,
Yes.
since pressure has increased, uh,
Yes.
temperature also increases. And
Great. Your internal energy increases. That's what you're gonna say, right?
yeah,
Perfect. Perfect. So that is what essentially happens. And these are the only two parts which were difficult. This is where students got it mostly wrong. If you got these two right, you had a great chance of getting full marks. Let's say if everything else you were doing right. Now, work done on the gas from A to B. What do you reckon is happening? What is the work done on the gas? Positive, zero, what? Negative,
mm,
A to B. I'm saying, what is the work done on the gas?
It will be positive.
Perfect. So since I'm decreasing the volume, I'm doing work on the system. So positive work is done. B to C, what's happening?
the system is doing work, so we're doing negative work.
From B to C, what is the change in volume? Is there any change in volume?
Oh no.
Exactly. So the work done is zero. So whenever you don't have a change in volume, work done is zero. If you have understood all of this, this is what I really wanted to cover with you guys. And this,
So work done depends on volume, and internal energy
exactly.
depends on temperature.
Yes, that's the rule of thumb. With those two ideas, you can just solve so many complicated questions. And thermal physics will often give you some really complicated questions. This is why you see these diagrams, pressure and volume diagram. This is why last class we extensively covered those diagrams. Go through those, understand those. So yes, good job. I feel like you guys have grasped the concept good enough. This is another question you can look into. You can just major in 2022 for one, and if you want to do this one as well, you can look into this as well. This part. Right now, I have gone 15 minutes over the class time, so I'm done. Any other question for today? I'm done. I will cover two topics, uh, which is this and the work done on gas, which you guys have understood by now. But I'll take 20 minutes, cover this, and move on to the next class topic, which is probably oscillation. Any confusion till now? All clear?
Yeah.
Great. So I'm done with today's class. Thank you guys for attending, and I'll end the class for today. See you guys on. Do we have a class on Thursday? Maybe check.
Will we have buffer class or
There's no buffer class for this week on Thursday, directly on Saturday, 23rd.
all right?
Great. So thank you guys. Hopefully no more question for today and I could explain everything. Great job.
So will
See
the
you guys
recording
on
be
Saturday.
posted like tomorrow or
This class,
yeah?
yeah, I will post this. I'll post this today. I'll try and post this today. Okay.
All right.
Okay. Great. See you guys. Bye bye.
Okay, thank you, sir.
No worries.